Hi, I'm Stephen Cass for IEEE Spectrum's Fixing the Future. This episode is brought to you by IEEE Explore, the digital library with over 6 million pieces of the world's best technical content. Today, I have with me our own Samuel K. Moore, who has been covering the semiconductor beat pretty intensely for Spectrum for, well, how many years has it been, Sam?
7 years, I would say.
Oh. So Sam knows computers down at the level most of us like to ignore, hidden underneath all kinds of digital abstractions. This is down where all the physics and material science that make the magic possible lurk. And recently, you wrote an article about the race to replace electricity with light inside computers, which is letting chips talk to each other with fiber optics rather than just using fiber optics to communicate between computers. I guess my first question is, what's wrong with electricity, Sam?
I have nothing against electricity, Stephen. Well, it knows what it did. But really, this all comes down to inputs and outputs. There just aren't enough coming off of processors for what they want to do in the future. They are electric, and electronics can only push signals so far before they kind of melt away, and they consume quite a bit of power. So, you know, the hope is that you will have better bandwidth between computer chips, consuming less power.
So it's not just a question of like raw speed, though, when you would talk about like these signals melting away, because I think that the signal speed in copper is about like what, two-thirds the speed of light in a vacuum. But then I was kind of surprised to see that in a fiber optic cable, the speed of light is about two-thirds of that in a vacuum. So you know, what's going on? What's kind of the limitations with pushing a signal down a wire? Sure.
A wire is not an ideal conductor. It's really resistance, inductance, and capacitance, all of which will reduce the size and speed of a signal. So, and this is particularly a problem at high frequencies, which are more susceptible to particularly to the capacitance side of things. So you might start with a beautiful 20 gigahertz square wave at the edge of the chip, and by the time it gets to the end of the board, it will be an imperceptible bump. Light, on the other hand, doesn't work like that. It has things that, you know, like there are things that mess with signals in optical fibers, but they work at much, much, much longer length scales.
Okay, great. So you talked about there are two companies that are in this sort of race to put like light inside computers. So can you talk a little bit who are they and what are their different approaches?
Sure. These are two startups, and they're not alone. There are very likely other startups in stealth mode, and there are giants like Intel that are also in this race as well. But what these two startups, IEEE Labs, that's AYAR, and I'm probably pronouncing it a little weird, and Avicenna, those are the two that I profiled in the January issue. And they're representative of two very different sort of takes on this same idea. We'll start with IEEE, which is really sort of it's sort of what we're using right now, but on steroids. Like the links that you find already in data centers, it uses infrared laser light, kind of breaks it into several bands. I can't remember if it's 8 or 16, but so they've got multiple channels kind of in each fiber, and it uses silicon photonics to basically modulate and detect the signals. And what they bring to the table is they have a really good laser that can sit on a board next to the chip, and also they've managed to shrink down the silicon photonics, the modulation and the detection and the associated electronics that makes that actually happen quite radically compared to what's out there right now. Mm-hmm. So really, they are sort of it's weird to call them a conservative play because they really do have great technology, but it is just sort of taking what we've got and making it work a lot better. Avicenna is doing something completely different. They aren't using lasers at all. They're using micro LEDs. And they're blue. These are made of gallium nitride. And why this might work is that there's a rapidly growing micro LED display industry with big backers like Meta and Apple. So the problems that you might find with a new industry are kind of getting solved by other people. And so what Avicenna does is they basically make a little micro LED display on a chiplet, and they stick a particular kind of fiber. It's sort of like an imaging fiber, it's similar to if you ever had an endoscopy exam, you've had a close encounter with one of these. And basically it has a bunch of sort of fiber channels in it. The one that they use has like 300, in this 0.5 millimeter channel, and they stick the end of that fiber on top of the display, so that each micro LED in the display has its own channel, and so you have this sort of parallel, path for light to come off of the chip, and they modulate the micro LEDs, just flicker them, and they do that. They found a way to do that a lot faster than other people. People thought there were going to be, real hard limits to this, but they've gotten as high as 10 gigabits per second. Their first product will probably be more in the 3 gigabits, kind of area. But it's really surprisingly rapid. People weren't thinking that micro LEDs could do this, but they can, and so that should provide a very powerful pathway between microprocessors.
Mm-hmm. So what's the market for this technology? I mean, I presume we're not like looking to see it in our phones anytime soon. So who really is spending the money for this?
It's funny you should mention phones, and I'll get back to it, because it's definitely not the first adopter, but there may actually be a role for it in there. Your likely first adopter are actually companies like NVIDIA, which I know are very interested in this sort of thing. They are trying to tie together their really super powerful GPUs as tightly as possible, so that they can, in the end, ideally, they want something that will bind their chips together so tightly that it's as if it was one gigantic chip, even though it's physically spread across 8 racks with each server having 4 or 8 of these chips. So that's what they're looking for. They need to reduce the sort of the distance, both in power, both in energy and in sort of time, to their other processing units and to and from memory, so that they kind of wind up with this really tightly bound computing machine. And when I say like tightly bound, I mean like the ideal is to bind them all together as one, but the truth is the way people use computing resources, what you want to do is just pool together what you need, and so like this is a technology that will allow them to do that. So it's really like the big iron people that are going to be the early adopters for this sort of thing, but in your phone there's actually a sort of bandwidth limited pathway between your camera and the processor. And Avicenna in particular is actually kind of interested in putting these together, which would mean that your camera can be in a different place than it is right now, with regard to the processor, or you could come up with completely different configurations of a mobile device.
Wow, it almost sounds like when you were talking about like this idea of like building essentially a computer, even kind of a CPU, even though many cores, but like on the size of racks. I was thinking of like that reminded me of like ENIAC days, or even like IBM, the IBM 360s, where the computer would take up several racks, and then we invented this cool microprocessor technology. So I guess it's kind of a sort of one of these sort of great technological cycles. But you mentioned there the idea about giant chips. That is an approach that some people are trying, like these massive chips to solve this bandwidth communication problem.
That's right. That is exactly, like they are trying to solve the exact same problem at Cerebras. I shouldn't say trying. They have their solution. Their solution is to never go off the chip. They made the biggest chip you could possibly make by just making it all on one wafer. And so the signals never have to leave the chip. You get to keep that really broad pathway all the way along. And then, your limit is just a chip can only be the size of a wafer.
How big is a wafer?
Man, it's 300 millimeters across, but then, they have to cut off the edges so you get a square. So it's a dinner plate, your face if you have a big head.
So what are some of the other approaches out there to solving this issue?
Sure. Well, if you look at IR and Intel are actually a good contrast in that they're really doing kind of the same thing. They've got silicon photonics designed to modulate and detect infrared laser light, and they've got, each of their lasers has, 8 channels or colors rather, or sometimes 16, I think is where they're moving to. The difference is that IR keeps its laser off of the chip, outside of the package with the GPU. And I should kind of explain sort of something else that is indicative of why this is the right time of it, and I'll get back to that. But my point is, IR keeps its laser off of the, like separate. It's almost like a utility. You wouldn't think of putting your power converter in the same package with your GPU. Electricity is sort of like a utility. They use laser light like a utility, kind of. Intel, on the other hand, is really gung-ho on integrating the laser with their silicon photonics chips, and they have their own reasons for doing that, and they've been working on this for a while. And so you wind up with a slightly different looking configurations. Intel's like just one connection. IR will always have a connection from the laser to the chip, and then out again once it's been modulated. And they each have their own reasons for doing that. It's kind of hard sometimes to keep, for instance, the laser stable if you don't tightly control the temperature it's at, and if you're in the package with the GPU. Do you have control over the temperature because the GPU is doing its own thing? Intel feels fine about this, clearly, and IR is just a startup, and they are just trying to get in with somebody who wants to integrate it into their own stuff.
Because that's something you've reported before on the challenge of integrating photonics with silicon, and so you don't have to go off chip. And there's kind of been a long and somewhat, I wouldn't say trouble, but a challenging history there.
Yeah, and the reason it's become suddenly less challenging actually is that the world is moving towards chiplets as opposed to monolithic silicon system on chips. So even just a few years ago, everybody was just making like the biggest chip they could, filling it up. Moore's law has been, not delivering quite as much as it as it has in the past, and so there's a new solution. You can add silicon by finding a way to bind 2 separate pieces of silicon together almost as tightly as if they were one chip. And this is a packaging technology. Packaging is something that people didn't really care about so much 10 years ago, but now it's actually super, super important. So there's 3D packaging type situations where you've got chips stacked on chips. You've got what are called 2.5D, which is really, it's 2D, but they're like within less than a millimeter of each other, and the number of connections that you can make at that scale is much closer to what you have on the chip. And then so you put these chiplets of silicon together, and you package them all in one, and that is sort of the way advanced processors are being made right now. One of those chiplets then can be silicon photonics, which is a completely different, it's a different process, manufacturing process than you would have for, your main processor and stuff. And because of these packaging technologies, you can put, chips made with different technologies together and sort of, bind them electrically, and they will work just fine. And so because there is this sort of chiplet landing pad now, companies like Avicenna and IR, they have a place to go that's kind of easy to get to.
So you mentioned NVIDIA and GPUs there, which are, you're really now associated with sort of machine learning. So that's what's driving a lot of this is these machine learning, deep learning things that are just chewing through enormous amounts of data?
Yeah. The real driver is that things like ChatGPT and all of these natural language processors, which are sort of a class that are called transformer neural networks. I'm a little unclear as to why. But they are just huge. They have just ridiculous, trillions parameters like the weights and the activations that actually sort of make up the guts of a neural network. And there's unfortunately sort of no end in sight. It seems like if you just make it bigger, you can make it better. And in order to train these, so it's not the actual, it's not so much the running of them, the inferencing, the getting your answer. It's the training them that is really the problem. In order to train something that big and have it done this year, you really need a lot of computing power. That was the the reason for companies like Cerebras, where they just wanted, instead of something taking weeks, taking hours, or instead of something taking like months and months, taking a couple of days, means that you can actually learn to use and train one of these giant neural networks in a reasonable amount of time, and frankly do experiments so that you can make better ones. I mean, if your experiment takes 4 months, it really slows down the pace of development. So that's the real driver, is training these gigantic transformer models.
So what kind of time frame are we talking about? Like in terms of like when might we see these kind of things, popping up in data centers, and then I guess when might we see them coming to our phone?
Okay, so I know that IR Labs, that's the startup that uses the infrared lasers, is actually working on prototype computers with partners this year. It's unlikely that we will actually see the results of those from them. It's not, they're just not likely to be made public. But when pressed, 2025, 26 kind of time frame, the CEO of IR thought was an okay estimate. It might take a little longer for others. Avicenna, their first product is actually going to be just sort of a low watt replacement for the between the racks kind of connections, but they promised a chiplet for on like in package with the processor sort of hot on its heels. But again, the customers are gigantic, and they really have to feel that this is a technology that is going to be good for them in the long term. So there aren't that many. There's NVIDIA, there's some of the giant AI computer makers, and some supercomputer makers, I imagine. So the customer list is not enormous, but it has deep pockets, and it's probably kind of conservative. So it may be a little bit.
Cool. And so to the phone?
Oh, yeah, I don't actually know. That's just right now. I think that's just sort of an idea, but we'll see if it things could develop faster in that field than others. Well, who knows?
So, is there anything else you'd like to add?
Yeah, I just wanted to kind of bring back that those two startups are like indicative of what's likely a larger group. Some of which are probably in stealth mode, and there's plenty of academic research on this, doing this in totally different ways, like using surface plasmons, which are sort of waves of electrons that occur when light strikes a metal surface. With the idea of being able to basically like use smaller, less fiddly components to get the same thing done, because you're using the waves of electrons rather than the light itself. But yeah, I look forward to honestly seeing what else people come up with, because there's clearly more than one way to skin this cat.
And they can follow your coverage in the pages of Spectrum or online.
Yes, indeed.
So that was great, Sam. Thank you. So today in Fixing the Future, we were talking with Sam Moore about the competition to build the next generation of high-speed interconnects. I'm Stephen Castro, IEEE Spectrum, and I hope you'll join us next time.